Hello, ladies and gentlemen. So finally, I decided to start streaming. Actually, it took me approximately a year to come to this state because it's science, it's not that easy. There are a lot of things to do in science, and also right now I have an application which I want to also promote by these streams, so there is a sense to do them because it's not only just enjoying science but also a promotion of focus structure tool. And I have here a chat box where maybe someone will write me some questions or just something and I can reply to it. I hope that right now there will be more than one viewers, at least someone will watch it. However, I didn't announce the stream in some social media because it's the first test stream. Only yesterday I have figured out how to work with OBS Studio at all and how to do the streams. But okay, let's try. So if I do like this, I guess then right now, yeah, you can see the condensed matter. So idea is that I can tell you how condensed matter works because I was studying for condensed matter for I don't know, like 3 years maybe, which was spread through a lot of years in my bachelor's and my master's, and right now I'm doing PhD. And here at the top you can see a chat which will be empty, but I still hope that someone can ask me something and it will appear there. Yeah, sorry. So I don't know, maybe it will take for an hour to overview condensed matter, and also you'll see this application better. Oh, sorry, I forgot to press one thing and disable notification. So here in this stream, I hope to just review what's going on in condensed matter. And also actually recently I was like revising like for several hours it, so I'm a little bit bored of revision by myself. So maybe in this format it will be more entertaining even for me. So what is condensed matter? Like from the structural point of view, we can answer this question by just naming structures which it has. And here is the list of all parts of condensed matter which I know yet, but it's just a classification. So approximately everything what happens in condensed matter is also presented here. Yeah, and maybe I should also step a little bit back and tell you about this application. So this is just like right now I will use this application only as an advanced PDF viewer. And maybe that's all what you need to know right now to understand the stream. So here, this is my note on condensed matter, which collects a lot of books, and my idea is to give you overview of some of them, at least of the topics that are covered in these books. And it's a big PDF because all subjects in physics are big, and a lot of things have been discovered during many years, like from 1940s, somewhere there. Like quantum mechanics was discovered in 1920s, so after it people started applying it to condensed matter, and so approximately from 1930s there were a lot of works about solid state physics, and that's why right now we have a lot of theory, and not to get drawn into it, I am proposing this application which will structure knowledge. And okay, just wanted to show you that it's actually a very big file. It has more than 3,600 pages. And the idea of this stream is to give you overview of what happens in general in condensed matter, and later in other streams I will explain some parts of it better. Of course, some of them I know better, some of them I know worse, and yeah, but it's not the goal is not to teach, because like there are lectures, there are clever professors who know condensed matter way better than me, but like few of them give just talks of this free format where we just discuss things. Yeah, maybe next time I should promote stream somewhere to have some viewers, but okay. Right now I still need practice, so okay. Fortunately there are 0 viewers, but it doesn't matter because I still enjoy this activity. Okay, so let's jump into condensed matter. So after spending more than 3 years in condensed matter, I have selected the following topics, and I will close for now this PDF. Just we will open it through this structure panel anyway. Just I wanted to show you that if we didn't have this application, I would be using just Adobe Reader or Google Chrome, another PDF reader. I would be clicking on these chapters and showing you and scrolling a lot, and that's way less comfortable than to use one structure panel where I can detach some structure windows, as you will see shortly. But okay, maybe we will return to this PDF. So condensed matter, as far as I understand, consists of several parts. Yeah, okay, also a little step back. So I have also a collection of formulas. That's how we can detach structures. Formulas about main topics and formulas about special topics which are not really used. And okay, this is a useful and comfortable way to work with like information, because I don't need to revise all the theory. I can just collect formulas, so they are not parts of condensed matter. They are just tools that make me working with more comfort. So there are several real sections of condensed matter. So everything starts with formalism, and formalism, it's really hard to discuss what's really a formalism of condensed matter, because there are different answers about the question. A lot of things are actually done in scope of the formalism. There are some general ideas which are very complicated, and it's very hard to even focus on these general ideas which are behind methods that are used. Then like some quantum mechanical approach comes into the game, and statistical physics also is involved, and yeah, it's like about second quantization, chains of atoms. Maybe I don't know what to comment about this. There are a lot of transformations if we just believe that there is a second quantization approach. and in some sense, condensed matter starts from second quantization. However, of course, we can do a lot of things without it, but these are typical like models from which a lot of physics can be extracted. Actually, there are a lot of models. There are, let's see how many pages I have. So I have more than 600 pages just about the formalism. So it's really hard to explain in some minutes what's going on here. But yeah, like we have basically operators, we have some ideas which give us this formalism of operators. Then there is a formalism. Yeah, there are some examples, and examples are important, and it's not like really a part of formalism, but they illustrate the formalism and they prove that we can do at least something. Also, like Abrikosov, Garkov, Dzelashinsky wrote beginning of their book by using examples. So that's why I also consider some basic examples as part of formalism, like basically just superfluidity, Fermi liquid, Bose gas. In some sense, statistical physics is also a toy model of condensed matter. Okay, we have a big method of Green's function, which starts from scattering approach in quantum mechanics, and then like the big part of whole formalism of condensed matter is the diagrammatic approach to Green's functions. And you know, these complicated diagrams, but we will see also them somewhere here. Just wanted to say that yes, this perturbation theory is used there. And okay, somehow it gives us linear response, which is purely from statistical physics, but okay, it's like still a big discussion. Okay, then we can ask like, what if something is time dependent? We can ask about extra properties. For example, what if we have non-zero temperature? Yeah, and that's like actually a very big extension of the formalism. And some mathematics is also there, but like I already imagined that if someone is not familiar with condensed matter, it will become complicated to really grasp this idea. So just wanted to conclude that in a nutshell, the formalism is about operators, like in quantum mechanics, but also then suddenly we switch to Green's function formalism, and there are a lot of extension of this formalism. For example, like what if we have also time-dependent phenomena? We also can discuss some examples of Green's function formalism. And there are a lot of examples. They're like very complicated, actually, not very obvious at all, and some extra features. Okay, but somehow there is just a formalism of condensed matter. Then also there are some typical phenomena. That's how I classify it. Other people classify it differently, but for me it's easier to classify it by some basics and some well-known phenomena. Yes, okay. Here there are just basics written. So first of all, we have lattice of a crystalline structure. Okay, we don't need right now to see the PDF because too much information will appear. But okay, we can classify lattices, and we can at least grasp the idea of how diffraction is used, how to get some properties of lattice. And here there are ideas just from Kittel's book of condensed matter. Okay, then after we learned what is a lattice, we learned that actually if temperature is non-zero, then atoms oscillate, and we classify these oscillations by introduction of phonons, that there are special modes. These modes have their properties, and there are a lot of theory about phonons. Actually, it's just an introduction that this concept is there. It's also very not trivial how to get to it. And the real value of chapter about phonons is that basically, if we want to get some real properties of material, like for example, someone comes to a theoretical physicist and tell him that, look, I have this material, can you use all your theory to predict something about it? So theoretical physicist would say, like, yeah, I have a lot of theory, and everything starts with like basic properties of matter, like phonons and electrons. So I need to know exact properties of phonons here in this material to plug it to my complicated formulas and get some predictions. So, like, if we are doing real applicable science, these are really essential topics. Yeah, then also there is electrodynamics, which is not really well written in this note, but still there are a lot of ideas which I assumed about polarization, about fields that are in matter. And okay, maybe it's another topic which goes beyond condensed matter, but still, like, some solid preparation electrodynamics is of course essential for real investigation of matter. Now finally we have electrons. So like, as I said before, idea is that okay, we have lattice, it oscillates, but these are just atoms. And what about electrons? Well, electrons can be, of course, in atomic orbitals, and they are already playing a role in energy between atoms of their interactions, how they are glued together because of electrons or virtual photons, I mean. And this is also written in later part of this note. But right now I'm speaking about free electrons that are not connected to atoms, that are just traveling through material. And um, there are a lot of things there, really, like energy bands, some models which are more statistical physical models of statistical physics, where we consider just free electrons. We can use also some theory of interactions of electrons, which is a Fermi liquid, but it's a really big topic, and we'll go touch this topic later in this review of condensed matter. But just I wanted to say that, yeah, also it's important that there are semiconductors, there are some Fermi surfaces. So semiconductor is a material which has special properties, like holes are there, and some special bands of energies are present in semiconductors. And of course, all our computers work on semiconductors. Yeah, and okay, maybe I shouldn't give too much details, but there are a lot of theories about just basic electrons, not with something involved, but just, let's say we have electron in a lattice. What do we know about it? And there are a lot of models, actually, abstract models which are not connected to some specific material, but and which don't have some exotic phenomena, but yeah, it's not a little topic also. Okay, finally we have electron-phonon interaction, and also formalism for interactions. And that's just a step towards complicated phenomena, because if we really understand how electrons in matter behave and how photons in matter behave, then we will answer immediately a question about how in general to describe electron-phone interactions. And here in the section of formalism, I didn't write it here because I was thinking about this formalism as just general properties. Yeah, it also includes, of course, interactions, but it includes it from some abstract point of view where we don't specify our model. I mean, for which material is it? It's written as like abstract model, abstract quantum field, theoretical, um, uh, like template models. So that's why formalism is of interactions is in part of like basics of lattice, vibration, and electrons. But again, it doesn't really matter how we classify it. Just for me, it's more comfortable to keep it here. And finally, there are a lot of things about magnetism. Okay, we have some typical models. Like basically, this is the theory from Kittel's book. That we have diamagnetism of free atoms, but in some materials it's also present. We have paramagnetism. Also, there are some theories like Pauli's theory of paramagnetism. Also, like Landau worked on diamagnetism. There is a famous Heisenberg model and like Ising model for ferromagnetics. So basically, typical magnetism is just collection of models. We have like around 5 models about magnetism, and that's already a solid preparation for studying something advanced in magnetism. But also, it's like a really big field of science. Here in this note, just some chapters are written because I wasn't studying exactly magnetism separately, but I just tried to write introduction. So okay, now we know what's going on in the formalism. Now we know what happens in typical materials which do not have some specific properties. Actually, I didn't check. It's also a good question how used this theory is. Like, does the theory really explains what happens in the majority of materials, or for example, no, and we really need some special theory? Yeah, I wasn't thinking about it yet, but I assume that it's so. So the fourth part out of 15, okay, out of 14 and -1 out of approximately 12 is a part about well-known phenomena, and I classify it as light matter interactions. So, for example, what would be if we shine light on our material? Then we have some specific materials, for example, if they are insulators or dielectrics, which is like a synonym of insulator. And I wasn't thinking recently about ferroelectrics at all. I just left here maybe because Kittel wrote. So yeah, by the way, I know that there are no viewers, but actually right at the top there is a chat where I hope next time there will be some questions. Yeah, okay. I'm thinking that, yeah, I'm just practicing. That's why I didn't announce it, but next time I should really announce the stream. Okay, there are such not very exotic but still special material, and we can also already play some games about using formalism to describe some of the materials. And I really don't think that one can really explain light matter interactions using basic formalism. So maybe I should add some also formalism for interaction with photons. But I wasn't really working much in this topic. But I was working more in topic about electrons and phonons, and this topic is really important because basically a lot of things happen because of electrons and phonons. Well, one of the most important examples is superconductivity, but superconductivity here is just makes us think more like, is this theory of electrons and phonons really used there or no? And right now I think that no, it's not used. But it's a really, so from one point of view we can say that electron phonon interactions is a key really part of condensed matter, because a lot of thermal properties are dependent on them. A lot of like conductivity is also dependent. There are a lot of special studies like polarons, charge density waves. And here I really hoped that this formalism will be enough to describe this. That was actually idea of this in part of formalism, to really understand everything here. But right now it's still in the development. But okay, like we know that phonons are oscillations of atoms, electrons are like well-known electrons. And if they somehow interact, there are really a lot of phenomena actually. Then there are some kinetic phenomena. I think big part of this chapter is written from the book by Abrikosov, but also, yeah, that's just purely from Abrikosov's book, Theory of Metals. And kinetic is like some really specific phenomena. I haven't seen anyone using this phenomena in some effects. But I think I met these people, they were just not mentioning these phenomena. So if electron hits something, then we already say that it's a kinetic process. For example, it can hit another electron. It can hit a phonon, or phonon can hit something, and that's how we have some thermoelectric effects. Yeah, and a lot of really specific effects. So in this little overview, it's better not to even touch what's going on there, but some scatterings are there. And then there are a lot of applications of kinetic equation, for example, for superconductivity, and for in general all non-equilibrium physics. And also we have some specific phenomena in magnetism, like spin waves, some specific cases of typical models, magnetic resonance, yeah, and like of course some oscillations if we introduce variable field. It's just my attempt how not to make a big section about magnetism. I divided magnetism into typical magnetism and special magnetism. Because as I said, magnetism is a really big part of science. It's like you can write like 10,000 page book about just magnetism. And by the way, you can write this book using this application, because we have select PDFs for LaTeX extraction, and you can choose some PDF and it will convert it to LaTeX automatically. And also you can import from archive. Yeah, so you just need to press to copy archive link, and we're also working on buttons that downloads all the articles. So yeah, it would take, if we manage to develop this app, I don't know, maybe an hour to create 10,000 page PDF, which has all information approximately structured about condensed matter or magnetism. Right now it's still in development, and it's not like, of course, as you might think right now, why do I need 10,000 pages of PDFs? Well, because you will have a good structure here, and this application, like focus structure tool, it's created because of just this idea. Like here you can see the key formulas, so you can be focused on them. See, like key formulas, you can add some your comments, but okay, everything you can modify, of course, but the most important thing is that you are focused already. Or here, if you want to have some extra formulas which are about topics which are way beyond basic topics, so you can be focused because you extract very easily key information, and you structure all the knowledge that you have. And that's the most important thing. That's because of this structuring tool, it's comfortable to work even with 10,000 pages. And if you have everything in one document, it's very fast to get information. And that's the idea of focus structure tool. If you have some comments, write them. But right now there are actually 0 viewers, so of course there will be no comments. But I promise that later I will be doing announcements of the stream. Okay, so there are some typical well-known phenomena, which is a really complicated actually part of science. Okay, this is not really working as I thought. I just wanted to show you how many pages have we covered in this little overview. Unfortunately, this application is not really yet developed, so we have some little bugs, or maybe I should recompile the PDF. Okay, so I can't show you right now immediately how many pages we have, but we have working PDF, so uh, I can little bit scroll and uh, and tell you that actually we covered approximately 1,300 pages right now in this overview. So let's move further. What's going on later in condensed matter? There are a lot of really a lot of things about transport. And I still have a question for a very long time. Why do we as scientists need so many theory about transport? And it's just introduction actually. There are big books about just mesoscopic transport, and I have my own big note about mesoscopic transport, and further we'll see some advanced topics of transport. And after spending maybe several totally months, maybe like totally 7 or 8 months about studying transport during last maybe 4 years, I unfortunately can't tell you exactly what's going on there. I know a lot of topics that, yeah, we have like Green's function formalism that is used to evaluate current. We have like linear response type approach, and that's like the thing that I didn't comment much, but it's here. It's like a big topic, so I don't know how to comment it in a short way. Just special formalism, which is better to consider as a part of Green's function formalism. So everything this is used for the um, uh, for the description of transport. So maybe if we take some special wires, then we can predict some current there. For example, like superconductors or junctions with superconductors. Or what if we add some disorder? Or what if we have a very tiny junction where only few electrons can jump through from uh, one part of it to another? There are some quantum Hall effects, of course. It's still a topic for a big book. There are some properties related to magnetic field, like what if we add a magnetic field. But basically it's about yeah, what happens with electrons? Maybe they localize, in a very special way, or maybe they scatter impurities and diffuse through the junction, through the wire. Also, there could be like spin orbit property of a wire, but I can't say that I really understand what's going on here, because I don't really feel like what is finally predicted, what is the outcome of this theory. There are like complicated formulas for current, but these are relatively abstract formulas. But still, like, transport and conductivity is a big part of condensed matter, and a lot of things are done there. There are some proposals of making some qubits out of wires, like Andreev spin qubit. But yeah, I still need to discuss transport with someone who knows it. Okay, now we are coming to the most well-known part of condensed matter. This is superfluidity and superconductivity. Superfluidity is like, of course, it was developed when people were thinking about liquid helium. Then, okay, a lot of things happen. For example, there was idea to uh, to use this superfluidity. Well, there is a book, Universe in Helium Droplet, which overviews everything what happens in superfluidity, and uh, so there are a lot of applications, and I'm aware not about a lot of them, about just a few of them, but even in cosmology, the superfluidity is used. And okay, so as far as I understand, superfluidity is uh, basically some special liquid. Uh, yeah, okay, we can of course say discuss some physical properties, that it say flows without resistance. But okay, from mathematical point of view, these are bosons of fermions which interact one with another, and yeah, maybe it's a bad title. It should be like interacting quantum liquids and superconductivity. Yeah, because I right now understand that actually not all Fermi liquids are superfluidous. And it's also a good question, which I haven't thought yet ever, after learning condensed matter for more than 3 years, that is there an example of Fermi liquid that is not superfluid liquid? I don't know. Well, of course, we have Landau's criteria of superfluidity, but one should like really apply it, and it's not really easy how to apply, because we need to know spectrum of the liquid, and uh, I don't have right now in my mind a lot of examples. But what is important is that we apply this theory of Fermi liquid, like interacting Fermi gas to electrons in material. And okay, there are some effects in condensed matter related to it. There is a Abrikosov Garkov book, which I was reading mostly about this topic. But also, okay, we can apply it to plasma. And Basel liquid is about another helium-4. And also, I actually am not sure what are the applications of the Basel liquid. But okay, these topics are really very famous in condensed matter, like classical topics. And right now, superconductivity is really the most famous topic. And I don't know how to really explain in a nutshell what's going on in superconductivity, because it's a really, really vast topic. Okay, maybe I can just jump through some approaches. So there is a Barton-Cooper-Schiffer theory, which is the most famous in superconductivity. And there is second theory, Ginzburg-Landau theory. And basically, these are two theories that you really just need to know in scope of basic preparation to superconductivity. And actually right now I can even open some PDFs like Ginsburg-Landau and BCS. If I wrote it, oh yeah, actually here there is a nice summary of all the theory that you just saw before. Okay, that's the Fermi liquid. Okay, I need to scroll. Uh, okay, I need to work out this application. Right now we don't have investors, so that's why a lot of things are not done in the application. Okay, these are well-known effects. It's better to open like this. Okay, the problem I guess is just I need to recompile this PDF, and the synchronization is not really good because there's like LaTeX PDFs, but I don't have time for this recompiling right now. I'm streaming. I should be more prepared, of course. Okay, yeah, basically that's the BCS theory. Right now there is no way I can explain what's going on here for people who haven't heard about it. But just to grasp main parts of condensed matter, I wanted to tell you that there is a Ginsburg-Landau theory, BCS theory, and some applications, for example, for tunneling. Yeah, and there are actually so many other examples which it's better not to mention, like what if there is external field that penetrates a superconductor? What if there is external voltage? A lot of theory is done about really junctions and tunneling, and there are some applications for special devices which are very which can be used as sensors of magnetic field because of their precision. There are some vortices of superconductors. As I was announcing before, there is a kinetic theory. Yeah, so the problem with superconductivity is that there is really too much theory about it, and too many questions are still unanswered about superconductors. Like, for example, there is a big field about disordered superconductors. And yeah, something about magnetism, which Abrikosov wrote. Of course, I wasn't reading what's going on here. Yeah, there are some theoretical features of theory of superconductivity. So just to tell you in a nutshell, really a lot of things happens in superconductivity. So in scope of basics, it's important just to know some just well-known established effects, maybe about the tunneling or about vortices that yes, they are there, or at least like how to describe disorder, because all models of disorders are very complicated and there are special really exotic tools about working with disordered systems. But uh, maybe it's important just to understand the idea how to describe disorder. Okay, that's interacting quantum liquids and superconductivity. Let's maybe close previous parts. Okay, the next part is very special, and I'm not going to speak much about it because it's still like a topic of whole book, and maybe I will review it more when I will be reviewing statistical physics. But yeah, basically we have Landau's theory of phase transitions, which is widely used for many phenomena, including superconductivity, but also for really the majority of phase transitions. There is spontaneous symmetry breaking. There are some theoretical investigations of like models. There is a normalization group approach, which is really used, but it's still a topic of more statistical field theory and not condensed matter. and I'm not really strong in phase transitions. I just know that a lot of things happen there. There are also quantum phase transitions, which I already discovered by Sabir Sachdev and a lot of other scientists. So in scope of condensed matter, yeah, like we know that if we freeze some material, it will have some, for example, phase transition to superconductor. Or if we add impurities, then there are some phase transitions to, I don't know, insulator. A lot of other things happen. So yeah, in scope of condensed matter, we have some basic understanding of what are the phase transitions. Yeah, also this is comfortable node to collect formulas, collect problems for practice. So it's a really what to tell you. So we have a lot of problems which can be used to understand better theory about lattice, about electrons, about semiconductors, about some non-zero temperature phenomena, about magnetism. And this is just a collection of the formulas which I was solving some time ago, or I'm just aware about these problems, because it's really impossible to solve everything. And some of them, like this one about self-energy and polarons, it just repeats theory. But if you think a lot about these problems, it takes a lot of time, but it gives you nice practice. So okay, that's not a real part of condensed matter, it's just a nice section to store useful also theory. I mean, not theory, but part of whole knowledge about condensed matter. Okay, then we have a collection of special formulas. Let's maybe just scroll through them and grasp some ideas. For example, what if we have special processes of phonons that they collide and interact? What if we deal with special diagrammatic approach for BCS, which is maybe not really used in some other places except exactly this place of derivation of the gap of superconductor, and so on, so on. That's the plot of the gap. Yeah, so these are relatively famous formulas, but relatively exotic approach to them. So not to pay too much attention, I just wrote it in this section, special topics in a nutshell, and I don't think about it if I don't need. Okay, we have also problems for practicing exotic and specific topics, because in these problems there were too many of problems already. So it's better to do two sections than one. That's why I have these two sections, because it was already, I don't know, 1,000 of pages. Okay, maybe 500 at least pages, which is too much really. And also, of course, we have numerical methods. There are different methods, like density functional theory. But okay, we can look at the text. Yeah. Fortunately, the structure is not that good. It should be a section, not a subsection. And I wasn't writing much in numerical methods because it's still a big part of condensed matter. And okay, soon I will write something here, but to come to numerical methods, it's important to understand really basics, like what are really like electrons, which properties electrons have, and so on, so on. So for me, it's not the first part of condensed matter on which I will work. And okay, I will conclude by the three last chapters. The first one out of these three is about exotic physical models. And there are really a lot of exotic physical models. That's why there is this section to just group them somehow, not to get crazy in them. Some of them are from Kittel's book, like non-crystallized solids. What if we have some defects, disorder, or like some liquid crystals, and like a lot of books are written just about liquid crystals, for example. Also, it's a very popular topic. What if we have low-dimensional material? Uh, yeah, like graphene, for example, and some other two-dimensional materials. Turns out that there are really a lot of specific models, like Dirac cone, Dirac equation. I'm not an expert in this topic, so I can't tell you right now why they are so used and how this theory is used, but there are some studies about them. There are some related theories here, topological matter, and usually it's really connected to low-dimensional models. Well, I classify, I just want to step back that there is a classification that we have exotic models, but physical models, which have some physical properties, and some exotic purely theoretical models. And physical models have at least some experiments that confirm that some of these approaches are really working and give good predictions for experiments. And pure theoretical models have, as far as I know, no experimental predictions. Yeah, it's like it can be a great science, but nevertheless, it's a purely theoretical model. So it's hard really to give an overview of what's going on here because they're really not so well classified. For example, like we have some optical properties, because of course I didn't tell much about light-matter interaction. There are so many things happen in science when, I mean in matter, when light comes to matter. And some of these phenomena here. There are some also here a section about van der Waals forces. Maybe here, but I'm not sure. Yeah, okay, maybe it's better not to mention this at all, but there should be somewhere theory from Abrikosov, Garkov-Zelashinsky about like radiation of particle that travels through solids, and there are also formulas for like forces that glue materials together. And it's a very nice but very complicated part. So it is a nice and very complicated part of condensed matter. But it's really special, and it's hard to, I don't know yet right now what are the physical confirmations from these predictions, because Abrikosov, Garkov, and Zelashinsky didn't write it in their book, so that's why I don't know, and I also wasn't focusing much on it. I don't need this topic right now. But yeah, okay, inner forces of solids, that's what I meant. Yeah, and actually that's exactly what I was thinking about. Um, but it's from Abrikosov. That's from Abrikosov, Garkov, Zelashinsky, yeah, van der Waals forces, and it's related to optical properties. I don't know, and maybe it's a bad title, but that's how they wrote in their books. Because polaritons, of course, like you shine light, it combines with phonon somehow, and somehow this combined particle propagates or decays, but has some properties that's really connected to external light. But this thing maybe is not really connected. Okay, maybe calculation of the electric constant is connected, but really I'm not sure. Who knows what's going on here? Yeah, in some other streams, if there will be more than 3 viewers, I will try to understand what's going on here. I understand it to some extent, but it's a really exotic topic. That's why I combined them into this topic, this part, which is relatively at the end of the note, not to think about these topics too much, because you can think for weeks and months and then get nothing in the outcome. But I hope that at least the majority of these models have physical predictions. And here, a lot of models do not have, as far as I understand, some physical predictions. Okay, maybe they do have because there are a lot of them. Something happens in nanowires, something happens in disordered systems. Okay, here there are just transformations and nothing is... okay, synchronization is bad. Okay, let's try to see what's going on there. Okay, it's because I didn't compile LaTeX. That's the only reason. Yeah. Okay, not to waste much time, I would propose just to show you the what's going on here inside. Yeah, I can also do like this, of course. It's not really hard. And here you see exactly what is in the table of contents on the PDF. So there are really a lot of things that is done about theory of condensed matter, and I really think that too much things are done. It's really hard to really understand what's going on here. Like strongly fluctuating spin systems, bosonization, Virasoro algebra. Yeah, it's better even not to look at it. Also, this synchronization is broken. You see, like, we don't have much budget to create this application. That's why it's not really done right now. But if we find some sponsorship, we will improve this application and there will be no such problem. So it's really hard to explain in a nutshell what's going on in exotic theoretical formalism and models of condensed matter. There are some also dead theories that are really just not used. Well, maybe it's better to say that in a nutshell, these chapters ask questions about what if some models have some properties. For example, what if there are some topological properties, or question about some just different properties, like what if there are non-equilibrium special effects, and for it there are a lot of special formalism. There is a lot of special formalisms, and there is a special note about kinetics, where there are some books about some Keldysh formalism or some replica tricks and so on. And some special transformation. There are special transformations of operators, because basically, yeah, maybe I got the idea how to explain it. So if you deal with formalism, sometimes it's not enough. Sometimes you try to work with Green's function method, but you understand that there is too bad explanation about how Green's function method works. And examples do not help, and even method of operators do not work. However, I don't know such materials, because like that's the problem of current science, that when we are given theory, we are not told what is the limit of applicability of this theory. But it's very likely that all these approximately 600 pages will not give you result if you try to use this method for some specific problem. So that's why you have, I'm not sure. Okay, let's look. But look, unfortunately, with some scrolling. Oh, but actually this synchronization works. The previous synchronization didn't work. So right now, after like 3 years or something, I have from 2000, okay, from approximately 3000 pages until 3500, so approximately also 500 pages of extra theory, and these 500 pages might help, but there are a lot of things that are not written in this note, like I have a 1000-page note about just topological materials. Also, there are 1000-page books about non-equilibrium matter, also 1000-page book about disordered systems and junctions and wires. Okay, I don't have much written here, so actually I have much more theory. And also, I wanted to use this moment to remind again what is the idea of this application, that if you structure the knowledge, then you really understand what's going on here. You can understand that something is in the basics of condensed matter, and if you think way more, then you can use some advanced method with big understanding that, okay, for this specific case, some basic method doesn't work, some easy advanced method doesn't work, so that's why I used that really advanced method, um, because like it makes sense, it's applicable. You can imagine, remember examples where this model used before and did some good results. So that's why structuring of information is really important, and that's why I'm like making this stream and promoting this application, because if we had this application for structuring information, then we would be way more productive, like 5 times more productive. Even this select PDFs for uploading, you select PDF, okay, like this. And you don't need to type LaTeX, you don't need to see, like, this article doesn't have any table of contents. How can you understand it? I mean, you can, of course, but it's way less convenient than if it had such a nice structure. And this application would extract this structure in like a fraction of a second. I can show you on a stream, another stream, how it works. But okay, like if we speak about pure theoretical models, there are really a lot of them. It's very hard to really classify it because some of them use some advanced algebra. Uh, like there is some base zoom in model or something like this. Okay, it's not really very well developed. I mean, the structure, because it's more a little bit convenient to use PDFs. Yeah, like also we have somewhere there the path integral approach. I think it's somewhere here. Uh, Basic formalism, advanced properties, and somewhere here there is a supersymmetry, of course. Yeah, Bosonization, path integral. Where's the path integral, by the way? Okay, it should be somewhere here, but anyway, it's also summarized here. Other well-known methods. Yeah, okay, you see like the problems that I wasn't using the path integral approach. That's why. Oh no, sorry guys, really sorry. Sometimes it happens. I haven't fixed it yet. It's also hard to track this bug. Really, I just want to find this formalism. Special topics. The synchronization is really broken. Usually it works fine. Yeah, so here, as you see, in chapter of special topics, it was putting me a little bit upper than I should be. There is this path integral method. Yeah, that's what happens when I don't check this synchronization before the stream. Okay, that's why, like you see, like why the structure is used, because I can switch very fast between topics. And here, if I were using just old PDF file, I would be just scrolling. Am I in the right place? No. Am I in the right place? No. No, and finally, uh, finally I miscrolled. Now I'm on the right place. Okay, how can I finally show you some path integral? I can click here, then click here. Now let's check if this synchronization also doesn't work. Okay, it approximately works, but not that well. If you want to improve this application, please write me. I have money, not so much, but enough to have some development. But it's not really important. It's not about money. It's about making a good application. Also, we have a pre-order button, so maybe we will have even money for good specialists. But it's really about the creation of really working application. If you know how to do it, if you are um, like enthusiastic about it, then you are the right person for us. So, okay, some things happens here when we write path integral. That's our measure over some extra fields that we're introducing, maybe by Hubbard-Stratonovich transformations. And so there are a lot of theory about it. I just wanted to show you that it's a um, part of special theoretical models, methods and models. And just in this overview, I wanted to show you that there is such part of condensed matter, which is a combination of exotic methods. And usually a lot of things are here not developed well. That's why they are not written well in my note, because few people really understand um, what is really meant by these methods. You need to do PhD basically in condensed matter to understand it. And finally, the last part of condensed matter is the properties of some specific materials. What if we have tungsten disulfide or V2O3, which properties it have? And there are some theories. I actually have also a big note about tungsten disulfide, because it has some different phases. For example, different theories were used for it, so you can write really books about just these materials. So in my note I just classified not classify, but create a little summary. And right now it's not written, approximately nothing is written here, maybe just one page or even less, because I have special notes about some of these materials. But it's a useful part of condensed matter, because if someone asks you, like, develop me a special device which has some, like, for example, great memory properties or good batteries, it can be used as a battery, or you can use like a solar cell or tens of other applications. Well, right now it's not really working, because people in condensed matter would say, like, hey, sorry, I'm doing theory, or I'm doing some that specific part, which is way, way far from these applicable parts. But my idea is that we can create a really strong formalism, and if we have one node where it has formalism and applications, then we can really be focused also on applications. We can see clearly which exotic phenomena maybe can be used for developing such applications, and we can write explicitly which are requirements are there for material to be applicable. So existence of this node benefits the whole node. I mean, existence of this part benefits the whole node really well. I mean, in ideal case. In reality, I don't have time to focus on these topics. Other topics are also really not very clear. There are really so much things that have happened in even basic phonons and electrons. So, and also it's also a matter of focus. So, right, we're called focus structure tool, and the main thing is to be focused. So here you can just select basic topics, think about basic topics, and then somewhere here there is some of your task and scope of your master's or PhD. For example, if you are given task about transport, you work out only this topic, and you have somehow some kind of awareness on other topics, and you can discuss them with some specialists. You can then improve all your understanding after these discussions. So it's a really pleasant way how to learn things, but you will never focus on some advanced topics if they are not in scope of your current task that you're solving. And we'll have some special tools that will help you be more focused, but right now we're not developing them because we want to even make this application work without such little bugs, without bad synchronization and so on. And basically that's all. There is some general overview in the appendix, literature collection, and of course bibliography. And of course all these topics that are here in this note, they are in the bibliography or in the titles, for example. Okay, here it's not written that it's taken from Kittel's book, but like for example here it's written that something is taken from Abrikosov's book about metals, and it's really important first of all for the author of the note, because it's sometimes hard, sometimes it's possible to forget where did you take a chapter from, uh, and like that's important to know where you took it, because it tells you how useful this theory is. If it's a theory which is written by Abrikosov, then it should be a good theory because he got a Nobel Prize, and no one ever in this community of condensed matter or world said that he did the bad science. He was a good scientist. He discovered Abrikosov vortices, for example, and many other things. That's why like it's important to write like where theory is came from, and this chapter at the end is just a collection of what is used, literature that is used, and literature that can be used in the future. And by the way, later we will improve these buttons, import not from archive but also do a web search, download the button, download the paper easily, and then put it to the place that you tell to put this application, or just at the end of this node, and then manually regroup or use AI tools for regrouping. Right now we don't have AI tools for regrouping, but we also don't have a budget to develop them. But we have a platform that approximately works, and that's already enough to tell you about condensed matter. So maybe the best thing what I can do is to just make a conclusion what happens in condensed matter, because a lot of things happen and it takes many years to just be comfortable with these methods. So first of all, we have some general methods that are approximately useful, but sometimes they're not useful. And it's really hard to understand where they're useful, where they're not, because usually people just say that, hey, we are working with this method and we're not going to comment anything else. There are some useless citations for you, which will not give you answers that you want, and you want answer about like, why do you use exactly this method? Why you're not using another method? Okay, but there are some basic methods. Some of them are in scope of just operators, some of them in scope of Green's function formalism, and this is the origin of some complicated diagrams and the whole diagrammatic approach. There are some subparts about like what if we have some finite temperature, or what if we have some time dependence or disorder. And this is like just extension of general formalism. Then we have some understanding of lattice, what is its structure, how we can detect and learn the structure from experiments. We know about vibrations of this lattice, and we can classify it somehow. There are some not so complicated phenomena of just vibrations of lattice. Also there are electrons that move, and also there are some spins that are related to some orbital electrons, and in some materials, because of some reasons, some effective models appear of magnetism. And there are like well-known types like diamagnetism, ferromagnetism, so on. There are some phenomena that are not so exotic. For example, what if electrons and phonon interact? What if some light hits your material? What if some collisions of particles appear, or some not that easy magnetic also properties are there, like spin waves, or some magnetic field is applied to material. Then there are models about transport, because still electron is moving through the material and current is there. Also there is a heat current, but I think heat current can be seen as just a little topic in scope of well-known phenomena. And there are different wires with different properties, like very narrow junctions, or I don't know, some special impurities. So that's why there are really a lot of theory about transport. And don't ask me, is it used or not, because I don't know. Then there are really classical, well-known theories about superfluidity, superconductivity, and interacting quantum liquids. Because it's a very natural question, right? We have bosons and fermions. So what if there is some interaction, or between them, or between them themselves, or between bosons and fermions? For example, superconductivity is exactly the interaction of two electrons through phonons, but it's really then complicated topic how really we need phonons, because if you take this chapter about lattice electrons and vibrations, then I'm not sure that it's possible to derive superconductivity. Like, some models are more like approximate model. Okay, then some phase transition can happen. There are a lot of phases of materials, and a lot of parameters are there. Some phases are not even understood right now by science. Then there are some numerical methods, which are really specific ones, and they give a lot of useful predictions. A lot of people really focused only on numerical methods in condensed matter. So it's a really important part, but as a theoretical physicist, I more focused on the analytical methods, because I don't know, for me it gives more clearness in what's going on in condensed matter. Then there are purely theoretical models and exotic physical models, because it turns out that the amount of phenomena is very big, and the amount of different models is also very vast. And if something unusual happens, we already know what can happen there if one learned these things. And there are special materials which have some special properties. Of course, there are a lot of thousands of studies, maybe hundreds of thousands of studies about materials, which property they have, so on. So that's in a nutshell the condensed matter. As I said, it's a very big part of science. It uses quantum mechanics and statistical physics. I don't know, it gives us a lot. Maybe, for example, computers, I don't know, superconducting wires, quantum computers, or maybe, I'm sure, okay, let's not discuss how quantum computers are applicable right now, but all of these predictions are based on some theory which might be connected to something that I wrote here in this book. I mean, connected from other books to this node. So that's the condensed matter, how I see it after approximately 3 years of working with it. There are still a lot of questions that I don't understand, but the main thing is not to understand everything, right? The main thing is to not get drawn in information and to understand what I need to understand. And right now, these are electron-phonon interactions for me. Maybe I actually even don't need to understand this. It's just my idea of really learning electrons and phonons. So some next stream, if there will be some viewers, I will discuss some things here. What happens with electrons and phonons based off Abrikosov-Garkov-Zelashinsky viewpoint, or I don't know, there are other theories like Abrikosov, like from Levitov-Shitov, parallels effect, that from Levitov-Shitov book about problems in condensed matter. So a lot of things happens in condensed matter right now in 2026. So thank you for your view, and yeah, of course there are 0 viewers except except my phone, but from where I see empty chat. But that was my idea to have a practice. Maybe later I will do the stream